me is a great pleasure to be here again and to tell you about present and the future of high energy physics with particle colliders, indeed the present and the future. So those are the topics that I will try to cover during this seminar. First of all, physics results from the Large Hadron Collider. Discovery of the 125 GeV Higgs boson, just a few things. Measurement of mass and couplings. Studies of spin and CP properties of this new particle. This is what we have been trying to do in run 1 with the run 1 data. And then not very much actually about QCD, electroweak, top and heavy flavor, because this will take a lot of time, but I will briefly mention a few things on this. So the point that I will try to make very briefly is that probably we can say today the standard model, I guess you know what the standard model is a complete theory. After the discovery of the 125 GeV Higgs boson, which is to date fully consistent with the scalar predicted by the standard model. Then I will briefly mention on new physics searches. Actually, I will not cover much about new physics searches. This will I will focus particularly to the Higgs sector, and I will tell you something about the excess that I think you are all aware of gamma on the gamma distribution with a mass around 750 GeV. Then I will try to start triggering the discussion that will follow up the seminar, trying to make the open questions that we have today in the standard model. And then the question that one of the more common questions today in physics, I would say in particular in high energy physics, what next? So I will try to mention briefly the luminosity upgrade of LHC and the future accelerator facilities. So where are today? Well, we can say that in July 2012, ATRA and CMS announced, this is now, we can say, part of history, the observation of a new neutral particle with mass near 125 GeV, which is compatible to date, as I said, with the Higgs boson predicted by the standard model. Now, the discovery of this particle has been made in these three basic bosonic channels. The discovery has been made, we can say, without losing too much generality, that has been seen searching for or studying the channels of Higgs in gamma-gamma, Higgs ZZ star for leptons, where the leptons here I refer to electrons and the muons, and Higgs to WW in the lepton-neutrino final state. We don't have yet any evidence, or actually we don't have an observation for the Higgs boson to fermionic final states. For example, Higgs to tau-tau. But this is not completely true, because a recent analysis, a recent work made by ATLAS and CMS, combining the findings, the independent findings of these two experiments on the tau-tau search, okay, has led to, in the combination, to the first observation of a fermionic Higgs bosonic decay, in particular indeed in the Higgs to tau-tau final state. So actually we should also take into account of this kind of new results. It goes without saying that it will be of master importance for ATLAS and CMS independently to continue the search for Higgs to tau-tau in the two experiments and to get the, say, 5 sigma of significance or more in each of the two experiments. This is just to give you an idea on how robust, simple, but also very, very clean. The channels that have been investigated in the discovery are reported, are presented by the detector. For example, this is a candidate of an Higgs boson decaying in 4 leptons. Actually, to tell you the truth, this must be an Higgs decaying in 4 muons. And the reason for which I say this is in 4 muons is because I can see here that the 4 tracks, 1, 2, 3, and 4, have been detected by this triplet of detectors. You see green, this triplet here, 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 and there, that are the muon chambers of the ATLAS detectors. By the way, I think I should also remind that the Pavia group, the ATLAS Pavia group, made an important contribution to the construction of these chambers. So in a certain sense, there is also the contribution from Pavia, for example, to this nice achievement. And this is the mass distribution that has led to the observation of the Higgs signal in the 4 lepton final states. Here I combine electron and muon final states. I plotted the invariant mass of these 4 lepton final states. And as you can see, in a situation where we have a standard model with no Higgs boson, we would have had the red histogram up to here, okay? And this is what we see, except, as you know, in this region here, around 125 GeV, we see an excess of data, okay? You see the data point here against the prediction which is on this red histogram, which is the indication of a production of a scalar particle in 4 lepton final state decays. Similarly for the Higgs to gamma gamma, the final state is even simpler than the 4 leptons. You have only 2 objects, even not tracks, because we are talking about photons. And the photons do not produce any track, except cases in which they may convert in electron-positron pair in the material of the inner tracker. But neglecting for a second this aspect, you have just say electromagnetic clusters with very clean signature, okay? Gauss combination, knowing the production point of the photons, you can reconstruct the invariant mass, and you obtain this histogram here for the invariant mass, where you can see that around, again, in a completely independent search, at around 125 GeV, we see a bump, which is consistent with what we have seen in 4 leptons, and which is consistent with the predicted standard model Higgs boson, assuming the mass which is only experimental measured. It's not predicted by the standard model. After these observations, ATLAS and CMS started to study the properties of this new particle, and we have investigated in particular the so-called signal strengths that are the rate of the production processes on the left or the decay final states. For example, if you take the final states of decay, you have a gamma gamma, ZZ, WW, tau tau, and BB bar. Those are the possible final states that would be produced by the decay of the Higgs boson, okay? And mu is just the normalization, is the measurement of the observed rate, or if you want, cross-section, but normalized to the one predicted by the standard model. In a world where the particle is produced or decays like the one predicted by the standard model, mu should be equal to 1. Any number different from 1, of course, taking into account systematic and statistical uncertainties, would indicate that this object is not consistent with the standard model. And you can see with current uncertainties for the production modes and the decaying modes, the object we are dealing with is consistent with the prediction of a standard model, of an Higgs boson of 125 GeV mass described by the standard model. Now, what you can also do, this is another way of presenting the results I just shown here on the production mode and the decay modes. You can go and try to estimate the so-called couplings. The couplings are, if you want, the parameters in the theory that gives you an idea of the intensity of the interaction between the Higgs boson and the elementary particles. Okay? And again, the couplings here are normalized to those predicted by the standard model, assuming 125 GeV. And again, also in this case, in the couplings, a prediction, a measurement which is 1 within errors would indicate consistency with the standard model. And this is what we see for the couplings of the Higgs to the Z boson, to the W boson, the top quark, the tau lepton, the B quark, and the muon lepton. Okay, so you can see that within errors, we are still in a situation where this object is consistent with the Higgs boson predicted by the standard model. Another way of plotting this, if you want, what gives you the Yukawa coupling of the Higgs boson, at least for the fermions, that it describes, if you want, the strength of the Higgs coupling to the particle as a function of the particle mass. The dashed line will be what predicted by the standard model, and the points is what we can say today. And you can see that at present, again, I said this many times already, there is good consistency with the standard model Higgs boson. I could go also in some detail, but maybe I can just flash briefly this slide. We have studied not only the production rate and the decay rate, we studied also the spin properties. Is this a scalar which is consistent with the, is this a particle which is consistent with a scalar object, spin 0, or 1, or 2? And okay, already with the Young-Mills theorem, you could exclude the spin 1 because you have the observation of this particle in gamma-gamma. But still, you could argue the discussion between 0 and 2 for the spin. And here, the results tends to indicate very much. You see that the data are much in the region of this orange regions, other than the blue one. This is just indicating you that our data seems to indicate that this object is more consistent, much more consistent with a scalar particle rather than a spin 2. Actually, in some models, the spin 2 is excluded. Now, Atlas and CMS very recently have also combined the mass measurements, okay? And with the run1 data, this is the result that we get from the Atlas and the CMS measurement on the Higgs boson mass, which is 125.09 GeV, with a systematic uncertainty, which is still dominated by statistics, 210 MeV, but soon with run2 and future data, we'll be able to reduce significantly this uncertainty, and hopefully we'll just limit it by systematic uncertainty that will be also reduced when collecting more data. So with this, with the discovery of this particle, and take into account that this object is consistent with the standard model Higgs boson, we can say that MH was the only fundamental parameter missing to completely set the structure of the standard model. And now we have really entered a new era, a precision test. Precision tests are now important, needed, in order to discover possible deviation from the standard model. with the discovery of the Higgs boson, the Standard Model is a complete theory. It's completely defined, okay, and can be used to, and data should be used to deeply probe to what limit, to what extent the Standard Model can describe the data collected in the labs, and in particular at particle colliders. There is not only the Higgs in the Standard Model, the Higgs boson. Here I try to summarize very briefly for you the measurement of the cross sections, okay, in this scale here, horizontal scale, for many different Standard Model processes, production of, for example, of dye boson or TT bar pair and so on and so forth. Compare, you can see the data are given by these symbols here, and the prediction from theory, from the Standard Model, is given by the colored areas. And you can see that graphically, of course, you have all the numbers you need if you want to make a quantitative analysis. With this plot, I want just to show you that the Standard Model is able to explain all current data in ATLAS and CMS at the Large Hadron Collider. We made a number of searches also, not only measurement in Standard Model. Here, I don't pretend you to go through, of course, this table. It's even not readable, but this just to give you the impression of this is a subset of searches in the SUSY domain that have been performed, okay? And in this diagram here, I try to give you the limit on the mass of the relevant SUSY particle, that is studied in each of these rows. And again, I don't pretend you now to discuss with you one by one all the rows that are in this table. It's impossible, of course, in a seminar. But this just to give you the idea that there is any single line where we can say we have seen an excess. We are just collecting a number of important limits. I say important because these data are progressively ruling out a number, fortunately or unfortunately, depends on your taste, are ruling out a number of BSM models, beyond Standard Model theories and models, that have been proposed long ago. With this, I don't want to conclude that SUSY is ruled out, but certainly the traditional SUSY models in which you have quarks or other particles produced at the scale of few hundred GeV and with a large transverse missing energy, this type of objects, this type of model, SUSY model, seems not to be favored by the LHC data. Nevertheless, you heard, I think already last year, that doing searches, we have some, say, excess here and there that are not completely explained. Here I report for you just an example. This is not the only one. It's the one that made most of the noise, that produced a lot of interest in our field, and also I would say outside our domain. Is obtained when you take two photons like you do for Higgs in gamma-gamma. With the difference that this time you don't study the, say, 100 GeV scale. You are more interested to go to higher mass, say, at the level of 1 TeV. And indeed, in ATLAS and CMS, left is ATLAS and the right is CMS, you can see that around 750 GeV, we have seen a bump, in excess of events that give a local significance in ATLAS of about 3.9 sigma local. Local means that you have to also consider that exploring a very large mass domain, okay, it may happen statistically that in some region you do have some fluctuation, downward or upwards, okay? So if you try to also take into account this effect, we can say that in this plot, the one, shown here, for Atlas, the global significance, the effective one that you should consider is 2 sigma. So it's something telling us that this is something interesting. We should continue to study and pay attention in particular with the new data that we are about to collect. Actually, we start collecting data not with very high luminosity yet, with the 2016 run. What next? So this is where we are today with the LSC data.
Can I ask a question ongoing, or should we do it?
As you... Why not? If it's some... Okay. So at this point, in this slide, I try to mention, to collect some of the open points that, to my opinion, are important. Please consider those is not an exhaustive list. I'm sure that each of you can add other points, okay? But those are among, to my opinion, are among those most important in high energy physics, in particular in the research conducted with particle colliders. First of all, is the Standard Model an effective theory? This is mostly for theoreticians, but still it's important. Of a more general fundamental theory, or it's rather already the final, is a sector, a well-defined sector of the final fundamental theory. Is this boson really the fundamental scala predicted by the Standard Model, or it can still be explained by other non-Standard Model theories? Of course, we have also to consider what is the nature and the origin of dark matter. We could have a relation between dark matter and the Higgs boson. We don't know. I don't have arguments to support this, but there are also no reasons to think that this is excluded. The hierarchy problem, or also known fine-tuning or naturalness. This calls for new particles to stabilize quantum correction to the Higgs boson mass. This we know. This is one of the fundamental, reasons that have somehow supported the theories like the SUSY one. But is this a real problem? Of course, the community here has not an unanimous view. Clearly, naturalness is desirable, but is this something we absolutely need? Question mark. It's not. Flavor problem. What is the explanation in the universe of the large dominance of matter over antimatter? And then I'm not going to list all other points that are there, starting from the origin of the neutrino masses and all the open points connected with the neutrino physics that are not covered in this seminar. So just to give you an idea, trying to study the Higgs boson couplings to elementary fermions and to elementary bosons. What is the level of accuracy that I need to reach in the estimation, in the measurement of these couplings in order to verify the consistency with the Standard Model or with other alternative theories? Of course, you can conclude the best possible precision in theoretical and experimental precision. But I want just to indicate to you that we have a possible expression of BSM theories and models, okay, where the coupling, for example, to vector boson of top quarks or beauty quarks, the deviation, depending on the BSM models you best prefer, are quite important at the level of 10%, of course, down also to few percent. And with this, the message I would like to give is that while for the run 1 LSE, we have not yet that accuracy, and this tells you the importance of a further investigation on the couplings, okay, of the Higgs boson. Already with the approved LHC program, physics program, say with 300 femtobarn, we can reach a precision in the accuracy which can be matched to what is possible to exclude by this, considering these models. Of course, higher precision would be required to have a better understanding of the comparison of data against standard model. Which tools to use in this investigation? So, of course, LHC is a real machine, is an existing machine, is a working machine, okay, despite the most recent accident, okay. So it's really the present and the near future in high energy physics, and everything has to do with this. And we cannot discuss any development for the future if not starting first with what we have seen or with what we will see soon at this machine. So the first concrete mid-term future option is, of course, the upgrade in luminosity of this machine, because this machine, if upgraded in luminosity, can give us the amount of data we need for precision measurements. Even in a very nasty hadron collider, like the environment like the one from LHC, we can still produce high-quality measurements. And then we have to discuss the far future open options. One option that now finally has been resurrected is, of course, the upgrade in energy of this machine, which is not in competition with upgrade in luminosity. We can discuss this a bit later. And then you have a plethora of very important ideas based on lepton colliders, in particular E+ E- colliders that can be linear or circular, or muon colliders. Okay? And then you have also, of course, the possibility of producing photon colliders without forgetting the important new idea, which is, of course, an upgrade of this machine, the Large Hadron Collider, in a new ring, which would be larger than the one we have today, and that would allow to reach an energy, say, a factor almost 10 larger than the present one at LHC. So LHC is the only high-energy particle collider in operation today, and it will be the only one for many years to come. There is no doubt. Even if this, just to explain you, there is not a direct competition with any of the future projects. This is the only machine we will have for many years, because any other project will require time, not only resources, financial and human, but also time. So this is the machine for the near term future. All future projects, nevertheless, should be based on the outcome from this machine, at least waiting for the 300 femtobarn. And at this point, and not by chance, is when the European strategy, the new European strategy will take place, we can have an idea on how to move the next directions. We have two possible situations after the other Large Hadron Collider at 300 femtobarn, the approved projects say. The LHC will not provide any direct observation of new physics at, say, 1 TeV scale, or new physics will be seen at LHC. These are the possible scenarios that we will be confronted with at the end of the approved scientific program of LHC. In both cases, the luminosity upgrade of this machine is the most realistic and sensible project to perform in the short term. So this, just to clarify, often the high luminosity is seen in competition with other projects. I'm just trying to show you, to explain you why this is not the case. Okay. Because if we do not find physics, new physics at LSC, then the precision studies of the 125 GeV Higgs boson sector, the precision measurement of the standard model in general, and the continuation of the search for new physics will be important also in this machine. And all this represent an essential input for any future collider. And let me say that we need a bit also to change mentality in high energy physics. Often we associate the, say, observation of new physics only with the discovery of new particles. Of course, this is the main path. If you see an excess, for example, if this excess at 750 GeV will be demonstrated is a physics and not statistics, or an artifact of the detector, then we are confronted with new physics. And this is the best way to go. But it's not the only one. And in particular, when a standard model that now is complete, and it's really there to be probed at the sub-percent level, possibly, this offers also the possibility of studying effects from new physics, looking to precision measurement done in the context of the standard model. So, in particular, this boson, if elementary, would be the first point-like scalar ever seen in nature. There are no other similar objects in nature with this property. Of course, you have the pi zero. Okay, it's a scalar, but it's not elementary. So we must look at it closely, and it represents a portal to a completely unknown new territory. The other option is that we find new physics at the LSE. Okay, so I would say at this point, here he said in a clean way, it will redesign the priorities of high energy physics. I would say it will make stop, reset, start. If we find new physics, we'll have to re-put everything on the carpet and rediscuss. Okay? In any case, whatever you will do, the observation of a new signal at LSE will need to be understood in order to see what is the new phenomena that we are confronted with. And with more data from LSE and its upgrade in luminosity, it will be important to validate with statistics the nature of the effect seen. And once this is validated, to study the properties of this object, at least with what the LSE can give you, and then helping you to design the project for the future. This in case option 2, the discovery, direct discovery of new physics. And an example is offered exactly by this excess. I mean, we need more data, we need to understand what it is, and if this will turn out to be physics, then I even don't imagine how many studies will be needed in the experiments, but also in theory, to understand what this guy is, if it will be shown to be physics. All this represents an essential input for any new future collider experiment. So the high luminosity LSE, I will not go into describe in detail the aspects, the main aspects of this luminosity upgrade, but we are talking about not only civil engineering, but also adding machine elements in the ring to achieve this luminosity. So the crab cavities, we need more powerful focusing magnets to achieve the beam quality we need. And there will be also some work done on the bending magnets to compensate the space that will be used by the new collimators. All in all, you can see this is the timeline. Basically, after say the phase 2, that would allow us to collect 150 femtobarn. We will move to a phase where the luminosity of the machine would be twice the nominal one. And then around 25 or so, there will be the last phase of this luminosity upgrade to reach the luminosity of 5 10 to 34 or 7.5 10 to 34 centimeters square per second. This has been already concluded by the European strategy in 2013 to be the priority for collider research in Europe. And this has been also concluded not only in Europe but also in US to be the that will be important, the full exploitation of this machine. And as I said, with a luminosity which goes from 5, maybe ultimate 7.5, 10 to 34 luminosity to collect about 3,000 femtobar in something like 10 years, or I say less, I hope. Okay, the challenge of this machine, there are many challenges, okay, but for this discussion I think one of the most important ones is the event pileup, is the superimposition of different anelastic proton-proton collisions on top of the one that has produced the proton-proton interaction of interest, where, for example, an Higgs boson has been produced. And this gives you an idea, for example, of the track record. This is a real event, zoomed in the central part of the CMS detector. There are 78 vertices reconstructed. Only one has, maybe you can see here, I think there is a famous Z boson, or something like this, that is produced together with this kind of noise. Also, for the upgrade of the machine, we will need also the upgrade of the detector. So it's not sufficient the upgrade only of the machine. We need to go also on the upgrade of the detector, because basically this pileup will pose severe problems to some of the current subsystem in the Atlas and CMS detectors. In particular, we will need a new inner tracking system and also some calorimeters components in order to have a detector able to stand the environment that we expect at high luminosity LSC. Now, very briefly, I would like to mention you the list of processes that can be studied at the upgrade luminosity of the Large Hadron Collider. And I can just, without reading all in detail, just many studies of the 125 GeV Higgs boson, which are the continuation of what we are doing already now, okay? And to this I would like to add the important study of the double Higgs production and the self-coupling, which is important to understand the structure of the standard model, the vector boson scattering, and of course, new physics searches. This is a part, or if you want, are among the most important elements of the physics program at the high luminosity LSC. In the Higgs boson sector, I just said what I collected in the previous slide, but in addition, I would like to mention that it will be possible, thanks to the large statistics that will be collected, to study also the differential distributions of the Higgs boson, and those are another important handle to understand whether the production goes as standard model expects or with different models. So, just to give you some idea of what we expect, if you take the Higgs 2,4 leptons channel, you can see this is the mass distribution that we expect with the background in this brown histogram, then the Higgs peak, and you can see the events per GeV in the mass spectrum that we expect to collect. This just to give you we will be plenty of data to make detailed investigation using this very clean channel, and just want to take your attention that here the signal to background ratio is quite good, is more than 1. And similarly, you can study the Higgs to gamma-gamma final states in association, for example, with production modes that will be fundamental for the understanding of the Higgs boson properties, namely with the TT bar system. This will give us the direct measurement of the Higgs coupling to the top quark, which is particularly important in the standard model. And you expect in one experiment to measure a signal strength of about 10%. But then there are also rare decay modes for which the statistics is tremendously is of paramount importance. Processes that are expected to be very tiny. For example, X2 mu mu. And I would like here to take your attention to the fact that one of the most, at least to me, impressive results of LSE is that we have not seen X2 mu mu. Lepton universality is something which we are familiar with. Take the Z boson. You see the Z to EE, the Z to mu mu, and the Z to tau tau with the same rate. This didn't happen. If the Higgs boson would have had lepton universality, we would have seen the Higgs to mu mu much earlier than tau tau, for example. And similarly for the Z gamma, these processes are important because any violation to this tiny rate predicted by the standard model, okay, would indicate presence of new physics, since it would not be explained by that theory. Okay, so the precision, the signal strength, this is just to give you why we need the statistics. This is what we expect in terms of accuracy on the rate measurement of different processes that are listed here for ATLAS and CMS studies made independently. And you can see that except for the bosons, okay, which are already quite well measured, but can be measured even better, okay, for the other processes like TT Higgs, which is important to be measured, we don't have a good accuracy. We are at the level at 100 femtobar, not collected yet, at the level of 65 also %. Only with large statistics like the 3000 femtobar of high luminosity, we can think to measure the strength at the level of 10% per experiment. Then you can translate, you can, I would say, convert the rates in the couplings, as we have seen already. And this is the ultimate, say, parameters that you want to study to probe the validity of the standard model. The Higgs boson couplings to elementary fermions and bosons. I'm trying to simplify and just to tell you that in this slide, I tried to summarize what we expect with 300 femtobar and with 3000 femtobar, the ultimate LSE luminosity, the accuracy per experiment of the measurement of the couplings of the Higgs boson to fermions and the other bosons. And please consider this as a model-dependent effect, as a model-dependent approach, because you should consider that at the LSE we cannot measure the natural width of this boson, and hence we need some theory assumption in order to make this type of evaluations. Nevertheless, we can measure couplings. This is the takeaway in the range of few percent to perhaps 7% accuracy, depending on the particle on which you are probing the coupling estimate. If you are not happy with the model-independent approach, there are good reasons for not being completely satisfied by this. We have also other scenarios under study that have been are considered, and that would measure coupling ratios instead of direct couplings in order to not depend from the natural width of the Higgs boson. This is in backup. In case of discussion, we can go and expand on it. Then I want just to flag an important study. I don't think I'm going to give all the details of it, of the Higgs self-coupling. This has to do with the so-called potential of the Higgs boson in the standard model, that in this theory is very simple, as a kind of a parabolic structure in the phi star phi term of this potential. You can see the parameter lambda and mu that are completely well defined in the standard model, okay? And one way, for example, to measure lambda, which gives you, if you want, the shape of this parabola, one way is to measure the lambda has to do with the coupling of the Higgs with itself. An Higgs, a virtual Higgs that can split into on-shell Higgs bosons. And this lambda parameter can be studied, for example, studying the production of a double Higgs boson in proton-proton events. Okay, so then I would like just to mention you, at the moment I'm just been talking a lot about precision measurements, in particular in the Higgs boson sector. But in one slide, I would like also to just make sure you are well aware that there is a large, quite extensive physics program for studies, actually for searches of new physics at the high luminosity LSC, as a continuation extension of LSC. And for example, in this table, this is just an example for a 5 sigma discovery, assuming the simplified model for the stop mass, the Guarino mass, the bottom mass in natural and CMS studies, by how much we would improve the discovery limit going from 300 to 3,000. The jump on the discovery, you see that goes from, I don't know, 1.0 TeV to 1.2 or 1.9 to 2.2. It's not huge. You cannot expect a great jump in mass, because to have this effect you need to upgrade in energy rather than luminosity. But still, the luminosity can give you some gain on the sensitivity at larger mass. The post-LSC era, many ideas are on the table. There are two main groups. Here I try to a bit to classify the ideas that are on the market to simplify a bit also the discussion. There are what I call the so-called Higgs factories, and here you can have electron-positron colliders, okay, that can be circular or linear, depending on technology, depending on many things, okay. Then you can have the photon collider. Sapphire is an example. I'm not going to present about this idea. Or muon colliders that are still in the family of the Higgs factories, but don't use electrons as colliding particle, but muons. Then there are also the very high energy hadron colliders that, of course, can produce not only Higgs boson in large quantities, but also be sensitive to new physics at the, say, 100 TeV energy scale. Okay, in the Higgs production lepton colliders, it's peculiar because in a plus and minus you cannot produce directly the Higgs boson, because the coupling of the Higgs boson with electrons, given that goes with the mass of the particle, is tiny. So you need to produce through the, say, Higgs Strahlung of a Z boson, which basically a virtual Z produce a real Z and Higgs boson. At muon colliders, the say rate is sufficiently, the coupling is sufficiently strong that you can think to produce the Higgs boson directly from the collision of muons. Of course, I don't think I need to remind you that muon colliders have not built yet. So this is something really for the future. So the ideas on electron colliders, electron-positron colliders, the FCC. Okay, this is the machine that probably you know the most. It's a new ring, 100 kilometers circumference at CERN in the Geneva region. It would go up to 350 GeV of energy. The circumference I said is 100 kilometers. The luminosity in 10 to 34 units is 5.1, and this is a very, very good project, very good proposal for the study not only of the Higgs boson, but also of high precision studies at the Z-pole. Then you have a similar project, but in China, CFC. The ring is almost twice smaller. The center of mass energy is 240, what you need to produce a Z and an Higgs together, okay? And the luminosity is slightly slower than the instantaneous luminosity, the one at least at the design level of FCC. Then you have the linear colliders. There is the clique idea of a linear collider starting from 500 GeV collision energy for electron and positrons. It can be upgraded up to 3 TeV with time, okay? The extension in length goes from the initial 13 kilometers for half TeV up to almost 50 kilometers in this design for 3 TeV. So we are talking about really huge, big tools, big facilities. Then the linear collider, the so-called ILC linear collider, the central mass energy, the nominal value is 500 GeV, but I should say that is now being proposed since already a few years at half of it energy, half of this energy, and and discuss an upgrade for later. And this will be hosted in Japan. Then the muon collider, which would, of course, yeah, for the muon collider you need at least a seminar. I cannot go through the details of the linear colliders, but just to tell you that this would be the machine that will give a direct measurement of the width, and not, say, inferred from the measurements that you can have in other E+ E- colliders. And this is something to be considered. Nevertheless, this is an extremely challenging machine. The muons, since are unstable, even taking into account the Lorentz factor, have to be produced, cooled, and collided before they decay in electrons. So this is extremely challenging. But there are quite a few ideas around on how to do at least initial studies for this machine. And then finally, the FCC Hadron-Hadron Collider will be the LHC, but with new magnets. And here the new magnets are the 16 Tesla niobium-3 tin magnets that would give you the possibility of reaching the 100 TeV in the tunnel of 100 kilometers, or if they are used in the LHC tunnel, it's another possibility. You use these magnets, okay, not just for the big machine, but for the tunnel we have already, which exists. And then with this you can reach about 30 TeV, about twice the energy of the current Large Hadron Collider. Almost done. So this is the final table, I would say. Here I give you in these rows the couplings of the Higgs boson measurements for couplings to the Z, to the W, to the fermions, etc., etc. For the different projects, for the high luminosity LHC, up down to the FCC EE with 10 atom bar and with 350 GeV energy. And this just to tell you that at the high luminosity LHC we'll have a few percent to 5% accuracy on the couplings, and with future projects we can go to the sub% level in the measurement of accuracy of these parameters for the Higgs boson. But this just to also again tell you how much competitive is in this point in time this machine for making the Higgs boson property studies. Conclusion. So with the discovery of the 125 GeV Higgs boson, a new era in the high energy physics just opened. The standard model, we can say, is a complete theory now. We need to test its validity at the highest possible theoretical and experimental precision. Nevertheless, it does not explain all observation in nature. New physics must exist at some energy scale, and we have to search for this new physics in direct and direct experiments. The Higgs sector is experimentally completely new, and its investigation may give you indications on where new physics could be. It goes without saying that direct searches remain mandatory. The LSC and its luminosity upgrade, high luminosity LSC, can shed light on the nature of this new boson at the level of 2%, and complete the search for new particles at the scale of the TV. And the decision on the next future colliders cannot be taken until we will not first see what will be the outcome from the Large Hadron Collider. The appointment is given with European strategy. WOS symposium is scheduled in 2018-2019. Thank you. Before starting with the questions, I would like to say that the LSC is almost back. We had an electrical perturbation caused most likely by this beech marten, okay? And this was the monitor of LSC this morning, you see, while I was on my way to Pavia. And just an hour before the seminar, the machine was in precycling. So let's hope that the data collection will start again by this weekend.